we have seen that the naive algorithm to solve the pair sum problem has a complexity that scales with n square. Now, obviously, we want to improve this because we saw that n square scaling is actually slow. But the question is, what exactly can we hope given that it's presently n square? Now, in this context, any algorithm that can help us cut down, let's say, from n square to n will be a significant speed up. So this is very strange. Previously linear search was n, and we said, okay, we should improve it to, let's say, log of n, or say square root of n with jump search, and then log of n with binary search. But here the situation is different. Here we are already at n square. From this point, if we can come down to n, then that's going to be really, really fantastic. Now, think about it a little bit. Basically, n scaling of n means that we are going to do as many comparisons as there are the items on the list as against, let's say, n square. And hence, basically this kind of becomes like in linear search, right? So linear search, we do as many comparisons as there are items on the list in the worst case. So any algorithm that can get us there is going to be a major improvement with respect to where we are today. And we'll see that when it comes to a sorted list with two-pointer technique, in fact, we will get there. In general, as it turns out, when we have a complexity of n square, in fact, there is one more complexity that lies between, let's say, better than n square, which is what is called n times log n. Now, this happens in sorting algorithms. As an efficient sorting algorithm will be one which will, let's say, do the job in n log n, but we will see this later. For now, our goal would be to go from n square to n. In fact, on a bigger picture, we are already seeing this, let's say, this relationship emerging. In search problem, we started with n, went to square root n, went to log of n. And then, of course, there's this O of 1, which is some kind of like, a constant time algorithm that doesn't depend on the input. There are operations, but, difficult to get there most of the time for practical problems here. Now we are kind of expanding that a bit. We are starting from n square. So we are saying that, okay, look, possibly I could go to n log n, but in this case, we'll go to n. Even n log n would have been seen as an advantage, as an improvement, but n definitely is an improvement. Now, if the list is not sorted, if the list doesn't have any structure, in fact, there's really not much we can do apart from getting more storage, similar techniques as hashing. So it's actually, the story is quite similar to the search problem. In the search problem, we argued that if the list had no structure, then, well, not much we can do. We have to stick with order of n, linear search. But then if the list had structure, we could do binary search, which was log of n. So we could improve, right? In the same way, in this case, if our data is sorted, as we'll see, we will use the two-pointer technique to go down from n square to a linear scaling order of n. And that, like it argued, is a great, great, great improvement in the context of this problem. So we will start discussing the two-pointer technique, the intuition behind it, the algorithm, from this point on, now that we have set up the entire, let's say, the basis of it. Do look at our website, www.ybyte.in, and enjoy programming. Take care. Thank you so much. Bye-bye.